A systems administrator provisions two local servers. He plugs them into the exact same physical network switch and then attempts to verify connection. He fires up a terminal and runs a standard ping utility. The request times out. The link lights on the hardware are solid green. The network cables are brand new, and there are no firewall rules active on either machine. The issue isn't a hardware malfunction or a broken configuration. The failure state comes down to a single typed sequence at the very end of an IP address configuration, a /25 instead of a /24. Without realizing it, the administrator has mathematically sliced their local network hardware right down the middle. One server believes its neighbor is in the exact same room, while the other one believes its neighbor lives on an entirely different network segment. Before we trace the mathematical error, we have to uncover the binary calculations that computers run silently behind the scenes to determine their own structural boundaries. So to understand how networks are divided, we must deconstruct an IPv4 address to its raw primitives layer. So an IP address, or Internet Protocol address, is a logical 32-bit binary number that's broken into 4 groups of 8 bits, which are called octets. So while humans write them in decimals, like 192.168.1.0 or .10, computers can read them as a continuous string of ones and zeros. So every single IP address is split into two halves. The first half is the network ID, and this acts as the unchanging identifier for the street your network lives on. The second half is a host ID, and this represents the unique house number that is assigned to an individual device on that street. So think of it like a corporate box office building mailroom. If a delivery comes in for 4th floor, desk 12, the sorting worker does not scan every desk in the entire company. They simply go to floor 4, and once they arrive at floor 4, then they find that specific desk. So the floor number is your network ID, and the desk number is your host ID. But how does a computer know exactly where the floor number ends and the desk number begins if the computer's reading ones and zeros? So it uses a subnet mask. A subnet mask is a mathematical filter made of a continuous sequence of binary ones followed by a sequence of zeros that defines the exact boundary line between the network space and the host space. So in modern infrastructure, we define this boundary using CIDR notation, or classless inter-domain routing notation. This is a shorthand form that uses forward slashes followed by a number to represent the exact count of consecutive binary ones masking the network space. This mechanism relies on a fundamental rule that computers use a strict bitwise AND operation to calculate their network boundaries instantly. So let's look under the hood to map out the exact mathematical clash that caused our two local servers to fail to communicate. So we'll convert the decimal setting directly into binary to help us trace the execution steps of the operating system's routing logic. So the /24 means that the first 24 bits are frozen solid as ones. So when we do our bitwise comparison, 1 and 1 is always going to be 1. So the output will reveal that server A resides on network ID 192.168.1.0. And we can see the working on the slide here. So it goes through and compares 1 and 1. Yep, that's 1. 1 and 1, that's 1. 1 and 0, that's 0. So we need two ones to have our network ID result in a 1. So the result of this is that server A concludes it lives on network 192.168.1.0. So now let's trace server B, which was mistakenly assigned the IP address of 192.168.1.150/25. So notice what happens in the very last octet. Because server B uses a 25 mask, the boundary line shifts right by 1 bit, stealing it from the host pool to lock down a more specific network space. When the bitwise end calculation runs, that extra 1 in server B's IP aligns with the mask, and this results in the network calculation equaling 192.168.1.128, which is a completely different network from server A's perspective. So this is the moment, obviously, where the communication completely crashes. When server A tries to send a packet to 192.168.1.150, it uses its own /24 mask and deduces that the destination is inside its local room. It broadcasts an address resolution request, and it expects a direct local answer. But when server B receives that request, it applies its tighter /25 mask, and its internal logic determines that its own network is 192.168.1.128. But server A is located back on 192.168.1.0. So server 2 concludes that server A is a total outsider. And instead of replying locally, server B drops the packet entirely or forwards it out towards a gateway router that isn't configured to send it back. So the state is asymmetric, unroutable, and broken now. So understanding this mathematical slicing is how network engineers design highly scalable, secure cloud environments like AWS VPCs or enterprise data centers. In production architecture, we never deploy massive flat networks where thousands of devices sit in the same broadcast domain. Instead, we implement variable length subnets to group infrastructure logically by security tiers. So let's have a look at an example of how an engineer would partition a standard private network block for a production deployment. So look at how cleanly we can slice a single network segment without overlapping IP space. By allocating a /26 to our public tier, we carve out 62 usable host positions. We can immediately start our internal application tier on the very next binary boundary at .64. So using a tighter /27 block to tightly match our 30 expected application nodes. And then finally, our databases are sequenced to a 28 block starting at .96. This gives them exactly 14 highly isolated predictable addresses. So enforcing these explicit CIDR structures directly at our routing interfaces locks down our broadcast domains, optimizes routing tables, and creates strict architectural checkpoints where firewalls can intercept lateral attacks before they reach our core data pools. So to summarize today, subnetting uses binary subnet masks and bitwise AND operations to mathematically divide continuous IP spaces into isolated logical network IDs, splitting the host and the network IDs. So this prevents routing conflicts and ensures security boundaries directly at the architectural level. So to test the knowledge or even research yourself, this is a question that I pose. A cloud architecture deploys a microservice environment requiring exactly 6 usable host IP addresses. What is the most efficient CIDR block preference, the slash, that satisfies this requirement without wasting unassigned addresses? And what are the exact network, broadcast, and usable host addresses for the very first subnet block if you begin at 10.10.10.0? So leave your findings in the comments, and thanks for watching.